All right. Okay, so our last speaker for today is Alvise Bastianello. Who's going to tell us about thermodynamics and transport in classical speed chains.
Thank you very much for the kind invitation. And I should set a bit of a stage because actually I'm coming from a slightly different community. I'm a quantum guy and a bit of new to all these classical systems. Okay, I also like classical systems, so studied them. But I started studying them from a quantum perspective. This means that my dictionary could be a bit off from what you have. So we try to fill the gap, showing a lot of pictures and appealing to physical sense. Okay, so it would be slightly different talk compared to the previous ones, maybe less mathematical sounding, but I hope that in the end will be understandable. Okay, so let me set the very general stage. Like again, projector doesn't work.
You need to click on the just on the slide once. Click on the slides. Maybe advance them.
I did it. Okay, cool. So let me set a general problem. I'm interested in the emergence of statistical mechanics or statistical physics in strong nonlinear medium. If you want, the idea is that I want to have a homogeneous system. For example, I randomly initiate some fluctuations, so on and so forth, and let it evolve with my dynamics. The beginning, everything will be a mess. Everybody's showing nice waves, so I want to be part of the crew. And in the end, these copied waves so relax to something. I would not really be interested in getting the fine details of the resolution, like a short time transient, but actually I want to focus on the stationary regime. In a generic system, you would expect thermalization. The system is so interacting with the ergodic, and in the end, everything should be described by a thermostatistical ensemble. So Maxwell Boltzmann exponential minus beta h. H is the Hamiltonian. This is for generic system. Generic means non-integrable systems, but if you are integrable, you have much more constraints that you should obey. Integral systems have infinite many conservation laws. I'm just writing them as QJ. And so as in the canonical case, the Hamiltonian is conservative evolution. And so you're going to have a Gibbs ensemble. In integral system, you are actually describing a stationary state with what we call in the quantum community a generalized Gibbs ensemble. But actually, if you just try to make a comparison, this is nothing else what you could be most familiar with, that is the integrable turbulence of Zucker. And it's just a formulation of the statistical properties in an operatorial manner. Okay. So in the end, I want to study this kind of objects, thermal or G's or interval functions. The general problem that this work is about, even though in the end it will be more focused, is understanding the statistical ensembles of classical integrable partial differential equation. Some motivations, well, of course, I shouldn't really stress it for this audience, but it's a fundamental mathematical interest. It is also very relevant for experiments. And I really like to show this plot, maybe mostly to the quantum community, but here I think it is nice as well. For example, in Schrödinger describes a full plethora of different systems, ranging from very classical systems like waves, optical fibers, are still kind of classical. You can go more into the quantum regime, maybe playing with condensates, maybe stuff that is not a condensate any longer, but still well described by semiclassical regimes. Eventually, of course, you break the fact that they are classical and you really need to go through quantum. For quantum means linear Schrödinger equation is not a good description any longer, but it needs to deal with equation on operator, quantum operator. Psi becomes an operator itself. I will not go into that direction. Something that I really like from my perspective, I'm a hydrodynamic guy. I like to know what is the large scale late time behavior of strong interacting systems. And the fact that we can really use classical systems as representative of different university classes for transport, thermalization, so on and so forth. In the end, if I look closely, I can distinguish having a system based on a spin or a tennis ball. But if I cross grain, I go to larger scale, both of them will look alike. Because hydrodynamics and thermalization are based on essentially the structure, the conservation laws, and symmetry. So we can use the classical system to understand the behavior of quantum systems as well. These are my motivations. Now, why I'm here talking about this problem? Because the canonical way to understand the thermal ensembles or generalized ensemble by the, I want to call it phenomenological solvent gas approach because it's slightly different from what has been discussed in the previous talks. I will try to make the comparison more clear. But you see that this approach is actually not always correct. If you dig in the literature, you're going to find a nice paper from the 90s, and I couldn't really find something more recent that is overviewing the state of the art for this solvent gas approach to build the thermodynamics on the same Gordon equation, but this actually applies also to other integral classical models. Just quoting, to summarize, I showed that the gas chronological description, the classical Sengol thermodynamics, breaks down at low temperature, even with a lattice cutoff. The exact figure, the classical physical mechanics of Sengol model is still a different question. There's something going on here, and of course, I will try to explain you and solve it. The talk of today, I could have chosen a lot of different nice classical systems, Riemann and Schrödinger, but today I want to talk about something different that is a more recent result. What I'll be interested in is a classical spin chain, the Landau-Lifschitz magnet. Okay, you should just imagine a real spin. By close, I can do a continuous approximation. They have to be aligned all together. You get some kinetic term, plus have a parameter that I can tune if I want to be more polarized in the z direction or in the plane axis. That is my data program. I got a Newtonian and the equation of motion. I hope the signs are correct, that I can swear about it. What are my motivations to study these systems? Well, this again comes a bit from the quantum perspective, but it can be appreciated by many of you, is the study of anomalous transport in integrable magnets. This is just a plot for a correlation function, magnetization, 2-point space and time correlation function. In generic system, you would expect a diffusive behavior, so a square root growth correlation. But from time to time, in these classical magnets, at the isotopic limit, you're going to see something different, like super diffusive behavior. And actually, we have the expert in the room, Jan, there, who can tell you more about it. But why I started studying the classical system? Because in the quantum case, we had a good understanding, analytic understanding on the quantum case, and the alcohol. But numerical simulation are extremely hard in a truly quantum system. On the other hand, is that in the classical case, we had numerical simulation, but not analytical framework. What we did here, here's this guy, give you an analytical framework to understand the classical system as well. And so now it would be possible to match analytic understanding against numerics, also for speech. Okay. How would I will proceed? This is a very simple roadmap of 3 different points. The starting station would be a quicker, very naive, physics ways introduction to solid gases and the application to thermodynamics. And in particular, I try to make understand what goes wrong in this description. Then I will try to fix this problem by using semiclassical limits. Warning, semiclassical limits have nothing to do with the semiclassical limits you can be used to, what like we hear in the previous talk. For semiclassical limit, I mean I really start with a quantum system, so in terms of operators, that in a certain limit can be well approximated by the classical case. The first letter, I do not know how to solve a classical system. I know how to solve the quantum one, and I will carry the solution to the classical one. Okay? This how, of course, there will be a lot of details under the carpet. I want you to understand the physics, happy to answer the mathematical questions, but let's leave the equation for later. In the end, I will tell you what is the result of this procedure for this spin chain and what we can do as an application. Okay? I won't really fix my focus spin chain, but if it happens, yes, you pass by my poster, actually the same techniques can be applied to the nonlinear Schrödinger equation. And in this way, you can obtain like a soliton picture, you can get something less and something more, but in the end, you get the same equation describing the nonlinear Schrödinger, both in the focusing and the focusing case. Happy to discuss that if you're interested. Of course, in general, first question is just interrupt me and let me know. So this will be my most technical slide for the talk. I just want to quickly review the finger sketching and how we could use it to try to understand the partition function and why it's difficult. So I'm just showing like, of course, the asparagus belongs to any integrable equation. I'm not using spin here, but just given scalar field for simplicity, but you can do it for speed. I'm going to write the transformatics. Eventually, that's in thermodynamics, so I don't really care about the boundary condition. I'm doing that in this limit where the system is very large, so boundary condition can be periodic, vanishing, I don't care. On the point of view analytics, it's better than vanishing because we know better how to handle it. The transformatics is nice because the first element is both the generator may constant quantities and also tell us what are the particles of excitation that belong to this. The point is that I have the constant quantities from this and increase by both the Newtonian and that's in terms of data. But if I want to compute a partition function from like fully perspective of integral is difficult, I could try to write a partition function and a summation of my normal modes that would be essentially the analytic properties of the A coefficient. But of course, it is hard because the measure is defined in the space of the real variables and not in the space of the spectral parameter. Doing this summation from scratch, I think that people do not know how to do that, but of course, at least I cannot. So we try to do something. Something different, I'm still reviewing literature here, is the phenomenological soliton approach. So it's using a soliton approach to compute the thermodynamics and the partition function. How does it work? Well, it starts with a very simple analogy. We know that we have solitons, an integrable system, is an integrable system. So solitons, upon scattering, they're going to feel some displacement after scattering. If you want, this is an analogy with a gas of hard rocks. And we know how to compute the thermodynamics of a gas of hard rocks. What is the recipe? Like that is the main reference. So first of all, we have to identify the modes. Are the solitons, are the radiation, are the water, the dispersion law, and the scattering properties, aka the scattering shift after the shift after scattering. And what does the scattering shift do? Essentially, as in the matter of gas, the matter particles have an extent, a finite extent, is stealing volume from the free space. In the solitonic case, it does the same. For the other of the effective length is fixed, instead for the solitons, depends on their properties, like their velocity, the speed, and so on and so forth. So in the end, one writes an effective volume and tries to do thermodynamics for these particles, not in the original volume, but for the effective volume that accounts for the finite size of these particles. Of course, that is not enough. I also need to give entropy to the gas. If I want to build statistical properties, I need to know what the entropy is. Naturally, there is I would say, reasonable answers for the entropy that can be written as a sum over the different particles, right? The quick factor is just normalization to make it like gauge invariant under transformation change of coordinates, and some entropy factor that I will call SI. And SI here is not determined yet. We need to understand what it is. And this is crucial part of the soliton gas phenomenology. Of course, once we would fix SI, we're going to get the entropy. The energy is simple to compute, and then thermodynamics will just be obtained by minimizing a free energy, as you do in standard thermodynamics. This gives you some integral equation for the density of state that from time to time you can solve analytically, other times numerically, but it's easy. And once you do that, you fix all the thermodynamic properties of your minimal system. Okay? So the crucial point now understanding the statistical properties. And I'm going to like show naive, yes. If you're gonna have a system with radiation, you would try to have a religious distribution. For me, theta is the Q considered. Okay. Instead, if you have soliton is the expert that is distributed with like a classical particle, so obeying Maxwell-Boltzmann distribution. If it is the case, these are the two choices we need to try. And what does it happen if you try to do so? Here there is a little model where this answer works and where it doesn't. Okay? It works on the defocusing or cosmic Schrödinger, on the Sich-Gordon model, on the KDB, and maybe others. Okay? The first two models have only a single relative mode. KDB has solitonic modes, but solid only one species of solid with a given velocity, but only one species. It does not work in the focusing Schrödinger single mode and the Landau-Lifschitz magnet. That is what I'm going to consider today. To understand why it's not working, we should identify the common feature of this model. That is the existence of solitons of very small height but arbitrarily large width. Okay? This is very dangerous when you do thermodynamics. Essentially, you're going to have solitons that are very large, and if I want to do thermodynamics, I need to put the system at finite size. So the finite size will try to cut away these solitons because it will be larger than system size. But on the other hand, thermal fluctuation are most likely to excite those particles because their energy is very, very small. So they will be very, it will not be much suppressed by thermal fluctuations. So we have something that want to put this more than something else that it does. And as a result, this in the end is why this doesn't work. Is essentially the most large solitons should be excluded for defined volumes, but I want to thermally excite them. If you would like to solve the problem by purely classical means, you really need to solve it at finite system size. It is difficult. I do not know how to do that. I will go for another route. Now we started with the observation that if I do quantum mechanics, the situation is different. In classical physics, solitons can have arbitrary, small or large, depends, but a continuous value of their size. Quantum mechanically, this object gets quantized. If you want, there is a maximum length of the soliton that the quantum system can have. And these are essentially quantized by the inverse of the Planck constant. So what is the idea now? We could consider a quantum system with solitons that have a finite size, take first a thermodynamic limit, everything will be well defined, and then after do that, take a semiclassical limit. This will give me eventually the right equations. This idea is not mine. I developed it a bit, but say it's mine that is the first reference. Why am doing so? It could be that it seems that solving a quantum system instead of a classical one will be more complicated. But actually, in the quantum world, we have a lot of machinery to do that. We have, if you want, the analog of the soliton gas picture. We call it thermodynamic meta-analysis. It is actually the same story, but it's taking is using the fact that the solitons are finite extent, plus there is no ambiguity on the statistics of the particles. In this case, you can show that the particles, their excitation should obey a Fermi-Dirac statistics. So we don't have the ambiguity that we have instead in the classical. Good. Let me apply it to the Landau-Lifschitz model. I will not show the details because there are a lot of calculations, but this is the procedure that we're doing. Thermodynamic meta-analysis. We have equations for the soliton gas and take a semiclassical limit. It exists a series of quantum interval chain of different spin lengths. The quantum case, the spin is quantized, can be 1/2, it can be 1, it can be 3/2, and so on and so forth. Okay. This family of models is integrable. It has a complicated dynamics, it's not really needed. But what we can do now is take a semiclassical limit of this object. To get a semiclassical limit, I don't want quantized spins, I want a continuing possible spin. To do so, I'm going to go in the large spin limit. If you do that, it's a combination of large spin and small cap in the quantum chain. What you're going to end up is this ugly list that maybe you do not recognize, but as soon as you go in the continuous limit, this Hamiltonian is just a Landau-Lifschitz model. So if you want, this complete Hamiltonian is an interval discretization of the Landau-Lifschitz in the continuum. Like we work on the lattice because it's more convenient, but in the end, what we are looking at is that model. Okay. We'll tell you the final picture. Which kind of excitation do we find? How the behavior? What are the consequences on the thermodynamics and right? The set of excitation, the species of excitation you can find depends on the result. In particular, if you are on the easy axis regime, on the easy plane regime, you're going to find different kind of excitations. And in both cases, excitations will have a statistics that is unconventional. It's not a statistics for soliton or radiation. It's modified. And you get it for free from this procedure. The easy axis regime, we're going to find a continuum of solitons. I'm using two real parameters to parameterize them. I have T lambda and a parameter sigma that essentially are the real imaginary part of the spectral parameter, modulus sum normalization. That is what it is. And the statistics is the statistics of solitons plus some additional terms that are not this constant or linear in the filling function, but it depends on species in the species. This I do not know how to get from classical meanings, it's just the result of this whole procedure. And here I'm trying to show something that is the dispersion and the dispersion of modes. You have the rapidity, the curves are the real part of the spectral parameter. The curves are referring to different values of sigma, that is essentially the magnetization carried by the solitons. This is the energy landscape. On the lattice, you get a singularity of the energy where it diverges, but because on the spin chain you have logarithmic interaction, this causes this divergence. But the thermodynamics is what the fact. Easy axis regime. In the easy plane regime, the situation is even more complicated because you still have a continuum family of solitons, right? Parameterized by lambda and sigma, very different representation of sigma. Plus, you get two extra modes. You get a relative mode of negative energy, radiation that is this green line here, plus a mode that is soliton-like, but is non-dispersive. The energy is just constant. So if you want, it doesn't have velocity, unless it is normalized by the interaction with the other particle, but in isolation, it would not have any velocity. This is the particle content. Of course, we can write the full equation for the thermodynamics of this gas in terms of certain gas feature. I will not do that because we know more or less what they are and they are at the distance. If you want, I can put it there. Now, how are we sure that everything is working? Because of course, it's a complicated procedure. Some checks. What we are doing now is computing the partition function, and from that, we are taking, for example, expectation value of observables. For example, if you are able to compute Z and VR, we can take a logarithmic derivative with respect to the chemical potential, for example, and understand what the magnetization is. We can do some analytical checks quite easily. Okay. For example, the infinite temperature regime is easy to compute from scratch from the partition function, just because the spins, all of them are decoupled. So it's just the physical single spin, which will rotate apart from a different way with the chemical potential. We get an analytic part of the magnetization that we can actually manage from this complicated procedure of solvent gas by solving analytically the solvent gas equation. There's another limit that we can understand, and it's quite nice. It is the case of strong polarization. Small spin fluctuation around a fully polarized case. If you want to just take the Landau-Lifschitz equation, you expand them, you linearize them, and you build a statistic of these modes. These are just non-interactive modes, are of relative nature, just radiation. We can get the result that we expect from the plane waves from this solvent gas feature prescription. Both in the easy axis in this plane, it is remarkable that in the easy axis case, our language has only solitons, but in the end, we can recover radiation in this field. Essentially, it is a cumulative effect of many solitons that they sum together and they behave as a unique relative mode. This is hidden in the equation, but you can analytically show. Analytics, two limits. Numerics, just taking Monte Carlo against a numerical solution of the solvent gas equation. And what you get is this comparison, the continuous line is the solvent gas against the Monte Carlo that is the sine laws. Okay, and I would say that the agreement looks pretty good. Okay. This is still thermodynamics. I promised some transport. I don't really have time to dig too much into that, but I want to show at least one slide advertise a bit. Also because we need to connect in the end to the solvent gas that we know, or also to generalize dynamics. We're gonna hear quite a few talks about that in a couple of days. So let me just shortly introduce it in this simple picture, but we know what the solvent gas is. If a system is weak and homogeneous on large scale, we can locally describe it with some macroscopic variables, the density of solitons. You can buy some effective equation for the evolution of this gas or solid. Okay, they assume the form that I'm writing in the slide. The missing index is just an index of the species. If I have many solitons, I have one equation for each soliton. If I have radiation, I also will do that, and so on. These equations are coupled by non-linearities in the practicals, but we know what it is. Okay, we can write it, but as a simple application to show that it works, because now that we know what the soliton gas thermodynamics is, we can now use this as a starting point to also look at the non-equilibrium and non-equilibrium properties. What we did here just to look at the 2-point correlation functions. The results based coming from general dynamics, but you can also convert them into soliton gas picture that allows you to tell to measure quantities like 2-point correlation function in space and time of certain quantities. And we can do it, for example, for the spin current and compute what is called the delay wave. That is just the spin current with the expectation value for network one with the integral, and that is not really an integral models that support ballistic clustering. In a diffuse system, that guy will be zero, in an integrable system is 0. This is the comparison. Again, solid line is the soliton gas prescription, and then the crosses are the Monte Carlo. There's bigger fluctuation because of course it's difficult to simulate also classically, but the method is quite convincing. And of course, all the limits of plane waves and so on, you can try them analytically. All right, can I win this time? All right, so let me conclude. Okay, the remaining time just sets the scale for the outlook, but I'll conclude in the beginning, I guess. So I try to give you a general story, then work in a factual example, but the general story is that the soliton gas picture to build thermodynamics seems to have some problems for those classical systems feature solitons of arbitrarily large extent. Okay? I don't have a general recipe to understand this from purely classical means. The only thing that I know is that I can solve it from taking semiclassical limit of quantum models, and the result is that you still get soliton gases, but with a statistics that is unconventional. It's not Maxwell-Boltzmann, it's not Regins, it's something else. There's a form that belongs to all these class of general systems, but the coefficients are model dependent. It would be very nice to have a classical derivation of that. I don't have it. If you have any idea, we can have it. Okay. The focus on a spin chain. I try to combine an inclination. I'm very happy about this work, but of course, if I try to understand the audience, you're more interested in reassuring. Okay, the same. And also in this case, you can play the whole machinery. Yes. I can change C, and indeed, my last slide before looking very quickly the outlook is just the summary of what you would get in the defocusing case. This was my poster yesterday, so I thought, well, it's in the poster, why show in the talk? But maybe people are interested, so I just show it. In the defocusing case, you get only one relative mode with conventional statistics, as I announced before. In the focusing regime, you get solitons, no radiation, doesn't enter species in thermodynamics. It's just a continuous soliton. Lambda and sigma are the real imaginary parts of the spectral pyramid. Models of particle Q that is jumping here and there. And the statistics is normalized. These are the equations you get from the minimization of the free energy. We're going to recognize here the scattering shift that the focusing case. And here instead is the focusing step, as it should be. Quickly, possible application for the Landau-Lifschitz, just because I'm excited about that. As I was saying, now that we have understanding the classical systems, we can use it to study anomalous transport and fluctuations in classical systems and hopefully learn more about quantum systems. A problem that for me is very interesting is what does it happen in the presence not only of conservation laws, but also of pH modes. If I take the Landau-Lifschitz model, I go to the isotope limit, I have an extra quantity that is, if you want to conserve it, the direction of magnetization, but is not coupled to a standard conservation quantity. Include them in a soliton gas picture or hydrodynamic picture at the moment is still up to debate. Finally, very interesting question about normalization, but I guess that is more concrete and my time is up. So we just thank my audience and thank my collaborators for this project. If you have any questions, let me know.
It's similar. I'm still not time to digest. You showed the transport equations, the U equation. You're to say. No, I cannot hear. Okay, yeah, I'm trying to. Okay, so you showed this continuity equation, the transport equation.
The hydrodynamic equation,
Rho T plus.
yeah.
Okay, but there is a second one, of course, the equation of state which connects.
So for me, rho is the density of solitons.
I would say it's density of states. So
Yeah, density of states,
yeah,
sorry.
because density of states, solitons is just in space, but it's also in the,
Yeah.
you have this. Well,
What I'm calling it is root density, but we're talking about
okay,
this amount.
yeah, but there is also an integral equation, of course,
Sorry,
integral equation connecting effective velocity with the density.
it's the same. I'm not showing it, but
Yeah. So I'm just asking you, you mentioned that something goes wrong for some systems because of these wide solitons. So what would happen is it something wrong with the integral equation?
no. The only thing that where there is some problem is really in the problem thermodynamics. Okay. So if the problem is giving me a time, the time in the state, there is a problem. If somebody has in the initial state, you can use all your mass equation, plug inside, and everything works. The extra part that you can get from this, I think, is that which mode they should include. Okay. So if you believe that the initial state is described by thermodynamics or generalizing ensemble, this tells you from this possibility the solitons, the radiation, and what else. And these are the three ingredients you can get from this. You can test in thermodynamics also if you just want to use this.
Okay, second question. So you mentioned for the defocusing analysis of gaining statistics is convention.
Yes.
Maxwell Boltzmann. How do you know?
Now, in the case, I know because actually
Yes,
you
yes.
read the paper as well.
That's why I'm asking.
Yeah, I know because I read your paper for the defocusing case. I know from two sources. One is myself, in the sense you do the limit from the quantum case, this is the question I get. But in the defocusing case, I've not seen for the defocusing initially, but I've seen for Sinch-Gordon, which is connected with defocusing, completely classical construction of thermodynamics, where the religion distribution automatically pops out. So for Sinch-Gordon is done, and for the nonlinear Schrodinger, you can just use that the semiclassical use of Sinch-Gordon. So if you have the first field theory, you get into the second. So there are these things. And also for Sinch-Gordon is just origins.
So you mentioned about the GTEs, but then when you did the calculation of your partition function, you only had the Hamiltonian and S3. So where did all the other conservation terms go? Yes.
The fact that of course, like you can think about the thermal ensembles as a particular case of GGs. Okay? The equation for the GG are actually the same, rather than having only the energy as a source term of my integral equation. At some point, it appears like a beta energy. I need to put beta energy plus beta one, the second charge, and so on. The problem is, in this case, that it's difficult to determine what these Lagrange multipliers are. Okay? So in that case, it's not really worth trying to reason in terms of Lagrange multiplier. What you're going to do is try to compute analytically or by other means to make the density of state. Okay. The fact is that also in this case, this construction tells you some, first of all, which modes you have to put. In second, it gives information asymptotic behavior of the density of state for small solitons. Small soliton means like large extent, but small amplitude. Because essentially, you need, let me just show from the Schrodinger that was here, whatever density of state that you have should be compatible with having this equation, the equation here. Okay, and this you can show that using important information, the limit of sigma is going to be equal to 0 because this guy here. If this guy here, my filling ratio, the density of state normalized on the total density of states, if you want, if this guy doesn't have the proper asymptotics for small sigma, the integral here diverges and everything goes up. So you should be careful computing this. If you just take the solution from the numerical solution of IST, that is enough to compute a lot of stuff. Also for the transport equation, the sorting gas equation works. But if you want to compute it, for example, the entropy that state, then you need to plug the right asymptotics in the center of the equation for instance.
There. So you consider this first the limit infinity and then each bar.
Yes.
And you said each bar is cycle. So
Is my quantum coupling, but in the end it is related to the size of the solid.
so is it correct to say that the limit of h tends to 0 corresponds to the one especially linear? So
No. It's really semiclassical limited from a purely quantum perspective. I tried to emphasize that it's different from the semiclassical limit that has been discussed for exactly to restore. Here I'm fully dispersive. I've been visiting the whole dispersion law, the classical system. The fact that there are my quantum model, there's not a okay, it cannot be reached my quantum model by putting a parameter in the Landau-Lifschitz equation and changing that. It's really a different model where fields are quantum operators and so on and so forth. They have their own dispersion law, they're complicated. In the classical limit, they go to the full classical model without any restriction or assumption. Indeed, for the you want to do the comparison, all the possible temperature and chemical potential for the analytic model was everywhere, and you also change of course the interaction. So there are no approximation on classical systems.
so you think those equations as those equations are leading over.
For the quantum model, but at the leading over the quantum of the semiclassical limit, but they are exact in the classical system. To give me Landau-Lifschitz, this is the exact description of thermodynamics, no assumption made on the Landau-Lifschitz, aside from the fact that I compute thermodynamics or generalizing it outside.
Okay, so I think we can thank Alvise again.